In this video, we're going to talk about magnetic domains and magnetization. So, when we talk about something being magnetized or having magnetic force, it begins with the atoms and the electrons specifically. So, we know back from chemistry that electrons orbit the nucleus of an atom. So we have a diagram of an atom here, very simplified, but it gets the point across of what we need. So we see our electrons circling around the nucleus here, each in their own orbit. Well, not only are the electrons circling the nucleus in an orbit, they are also spinning or rotating on their own. So we have electrons moving around in an orbit, and we have them spinning. So electrons are charged, they have a negative charge, they are orbiting the atom, and they spin. All of these things together means that every single electron is a tiny magnet. Now, electrons occur mostly in pairs, and these pairs have opposite spins. So if we look at this loop right here, it has two electrons in this orbit. Well, each of these electrons is spinning in a different direction. So this one is spinning this way, and this one is spinning this way. So they have opposite spins. Now, opposite spin electrons cancel out each other's magnetic effects. They have opposite magnetic effects, and therefore they cancel out. Most materials have most of the electrons in their atoms paired up, and therefore most materials have very weak magnetic fields. You'll see this if you've ever taken a magnet and tried to put it on like wood or, a plastic cup or something like that. It won't stick. That's because the atoms in those materials have very weak magnetic fields. But what about materials with unpaired electrons? So, we'll get to why there's ants here in just a second. Unpaired electrons produce magnetic fields because they don't have anything to cancel them out. So you have an unpaired electron or multiple unpaired electrons in an atom or material, and they produce magnetic fields. Usually, when materials have one or more unpaired electrons, their atoms' fields don't line up, making an overall weak magnet. So we're going to bring this to the ants here. Most of the time when we see ants, they're all kind of crawling in different directions, okay? So we think about that as just typical in atoms with unpaired electrons. The magnetic fields don't line up, making an overall weak magnetic field. However, if a bunch of atoms' magnetic fields align, that creates a magnetic domain. So I'm sure you've seen it before that maybe like you put some food down here or something, all of the ants are going to start moving in the same direction. So they normally move kind of chaotically and randomly, but it is possible for all of the ants to move in the same direction. Same thing with these magnetic fields. It is possible to align them. When they align, we make a magnetic domain. A magnetic domain is defined as a region that has a very large number of atoms with aligned magnetic fields. Magnetic domains have strong magnetic fields. We're adding together all of these small magnetic fields, and they make a strong field. Now, magnetic domains, this sounds kind of weird, but actually if you look at magnetic materials under the right kind of microscope, you can actually see the magnetic domains in something like iron. So what we're looking at here is a bunch of different magnetic domains. So materials like iron, nickel, and cobalt have enough unpaired electrons, and the atoms make magnetic domains. So this creates what was called a ferromagnetic material. This is a material, such as iron, that can be magnetized because it contains magnetic domains. Okay? So if we have a bunch of magnetic domains, just like the magnetic fields before them, magnetic domains have a direction. If the magnetic domains are randomly arranged, you're not going to have a magnetic material. It's not magnetized. But if we align most of the magnetic domains going in the same way, your material does become magnetized. So we have an example here. We have a bunch of magnetic domains, and you see all of their magnetic fields are pointing in different directions. This results in all the fields canceling each other out, and you have an unmagnetized material. However, if we align all of the magnetic fields, or most of them, then all of the magnetic fields are working together, and you end up with a magnetized material because the magnetic fields kind of combine and create a very strong magnetic field. Now, let's talk about how you make something magnetized, because, you have a nail. That nail is not just automatically magnetized. You have to do something. So, if a non-magnetized ferromagnetic material is placed in a strong magnetic field, it will cause the domains to align. So we have something like just a nail here, for example. All of the magnetic domains are pointing in random directions. However, if we introduce a strong external magnetic field, so we put this nail under a really, really strong magnet, the magnetic domains will align with each other. Okay? So that makes the material become magnetized. However, as soon as you remove that strong magnetic field, atoms are constantly moving, and so the domains will become disorganized again, and the material will not be magnetic. You can see that right here in C. When it's in the magnetic field, all of the domains are perfectly aligned. Once we remove the strong external field, the domains just become slightly reverted to their original form. So over time, they will completely revert to being random, and they will not be magnetic. So if you take a piece of metal, or if you take a ferromagnetic material and you place it in a weak magnetic field, you will have temporary magnetization. The magnetization will not last very long because they did not get ordered enough. However, if you place it in a strong magnetic field, you will have quote-unquote permanent magnetization. Now, permanent magnets are not actually permanent. They will ultimately revert back to being non-magnetic, but they will last for a while. And so it just takes a lot longer. For the sake of argument, we call them permanent magnets. Now, if we cut a magnet in half, this will make two new magnets with north and south poles. So if we look here at our magnetic domains, all of them are facing up here. So if we take this magnet and we cut it in half, well, first, up here would be our north pole, down here would be our south pole. If we cut this magnet in half, we will end up with a magnet here up where you still have your north pole, and down here is going to be your south pole because the arrows are all pointing up down here, and so the bottoms of the arrows are here. On this new magnet down here, all of the arrows are still pointing up down here, and the bottoms are down here. So your north pole will be here, and your south pole will be here. So if you cut a magnet in half, it makes two new magnets with north and south poles.